This video is confidence intervals for estimating a population mean when the population standard deviation is not known. So, in reality, if you were trying to estimate a population mean, most likely you don't know the population standard deviation either. And so when we've been estimating the population mean using confidence intervals in our previous videos, they gave us a population standard deviation and we used that in our formula. However, in practice, this is usually not the case. Usually you won't know the population standard deviation, so we've got to think about another way to do this. So if the sample is large enough, we can use S instead of sigma. So what does that mean? It means we can use the sample standard deviation rather than the population standard deviation if the sample size is large enough. But when we have smaller samples, such as samples smaller than 30, this breaks down. So instead of a confidence interval using the formula here, which we need a square root sign. That was the formula we learned previously. Instead of it looking like that, we're now going to use one that looks like this. So notice the things that are different. We have replaced the sigma, the population standard deviation, with S, the sample standard deviation, because we might not know the population standard deviation, but if we have collected a sample and we found the sample mean, then we either know or we have access to the sample standard deviation. So that will be known. The other thing that we have replaced, instead of our Z critical value, we now have a T critical value. So the question becomes, what exactly is T? So notice so many similarities, just a few things we've swapped out. If we swap out the sigma for an S, you got to swap out the Z for the T if your sample size isn't big enough. So the T comes from something called a T distribution, and it's the distribution that we use if we don't know the population standard deviation. It is similar to a normal distribution. It's just shorter. However, when our sample size increases, the larger it gets, the T distribution actually changes and it gets closer and closer to the actual normal distribution. And I've illustrated that here. The black curve is the standard normal curve. So you can see that's the tallest curve here. That's the standard normal curve. But for the T distribution, notice I have three different ones. Notice how it's changing. So let's talk about how it changes. Well, the first one, you'll notice it is shorter. The brown one is shorter than the black standard normal curve. And its height really depends on what is called degree of freedom. Now, degree of freedom is directly related to sample size. So if it's got a small sample size, it has a small degree of freedom. So notice here, the degree of freedom is only 1, and it's fairly short compared to your standard normal curve. Also, look at the tails. That's the outside parts of the curve. The brown tail for the degree of freedom of 1 is higher. It's thicker than the black tail for the standard normal curve. So for T distributions, the curve is shorter and the tails are thicker. But let's look what happens to the peak and the tails as our degree of freedom increases. When we increase to a degree of freedom of 4, our peak has gotten higher. It's gotten closer to the standard normal curve, and look what happens to our tails. Our tails are getting thinner. You see that? It's going lower on each side. When we increase our degree of freedom up to 10, it's even taller. This time, it's almost as high as the standard normal curve, and your tails are much thinner. They're almost as thin as the standard normal curve. So the bigger your sample size, the bigger your degree of freedom, the more like the standard normal curve your T distribution becomes. So degree of freedom, here is a formula you need to know. Degree of freedom is n equals 1. I'm sorry. Let me repeat that. N doesn't equal 1. I'm repeating this. Degree of freedom is n minus 1. N minus 1. So degree of freedom, you take your sample size. So if we had a sample size of 10, the degree of freedom would be 9. If you have a sample size of 20, degree of freedom is 19. If you have a sample size of 35, your degree of freedom is 34. So the more the degrees of freedom, again, as we said, the more degree of freedom you have, the closer to the normal distribution your t distribution becomes. The mean for the standard t distribution is 0, just like for the standard normal curve. That hasn't changed. It's still bell-shaped and symmetric. That hasn't changed. And again, the t distribution compares with the normal distribution in that it's shorter and it has thicker tails. And we assume for the t distribution that the population is normally distributed. And the meaning of t critical value is similar to the meaning of a z critical value. We just have to go about finding it a slightly different way. So one way is using a table, and the other way is using a calculator. However, the calculator that can be used for this are the TI-84 pluses and up. So if you have a TI-83 or a regular TI-84, you might not have the function in your calculator to find your t. And if that's the case, you have to learn to use this table, which I can get you a copy of if you need it. So let's see how this works. So let's say we have n equals, let's say 16. That's our sample size. And our confidence level is 98%. Okay? So we're going to go down to the bottom here and find 98%. That's here. 98%. And we are going to go up to our degree of freedom. Now our degree of freedom is equal to 16 minus 1, your n minus 1, which is 15. So what we're going to do is we're going to go up to 15. Oops, didn't mean to highlight in black. All right, 15. So what we do is we go up the column that says 98%. And we find the row that says 15, and then we find their intersection. So the intersection would be 2.602. 2.602. So our t critical value is 2.602. So again, find your confidence level on the bottom and then go up to your degree of freedom. Degree of freedom is not your n, it's n minus 1. Now notice really quick, the degree of freedom goes from 1 to 30. Once you go past to 30, it skips to 10. It skips 10 to 40, then it skips 20 to 60, then it skips 20 more to 80, 20 more to 100, then it skips to 1,000. So here's the deal. If you have a degree of freedom that's higher than 30, then what you're going to do is you are going to go to the next lowest one. So if your degree of freedom is 35, you will use 30. If your degree of freedom is 42, you will use 40. If your degree of freedom is 59, you will still use 40. If your degree of freedom is 99, the next lowest is 80. You would use 80. If your degree of freedom is 250, The next lowest one is 100. That's the one you're going to use. Anything above 1,000, you're going to use 1,000. Okay? Now, notice here what happens after 1,000 is the next row says Z. So this is the Z critical values for 9. If you were to do the INV norm in the calculator for 98% confidence level, it'd be 2.326. This is going to show you how the higher the degree of freedom, the closer it gets to actually being the same numbers you would have on a normal distribution. So anything above 1,000, just use, actually, I think I said anything above 1,000, use 1,000. So for 1,001, the degree of freedom would be 1,000, use that. Anything above 1,000, though, for degree of freedom, use the Z. Use the Z. Okay? Alright, so find the critical value to construct a 90% confidence interval based on a sample of 7 items. So if we have n equals 7, degree of freedom is 7 minus 1, which is 6. So we are going to go to 90%, and the confidence level is 90%, and the degree of freedom is 6. And it looks like right here, 90% goes up to 1.943. 1.943. Okay? Now, if you have this version in the calculator, it's called INVT. You get there by going to second bars and choosing number 4 INVT. It requires 2 inputs, the area and the degree of freedom. So if you were going to do this, if 90% is in the middle, okay, that leaves 10% on either side, so 5% here and 5% here. Now, one way you can do it is second vars INVT. You'd put in the area to the left of the lower boundary, which is 0.05, and follow it with your 6. That's going to give you negative 1.943, which is the same thing that we got on the table, except we'll drop the negative sign. The other way to do it is you put the area to the left of the upper boundary, which is 90 and 5 together, which is 95. So they put in 0.95, and then INVT was 6. I'm sorry, the degree of freedom was 6, and you still get 1.943. So whether you are able to use the calculator or whether you use the table, you will get the same answer. Okay, so we're going to stop the video here, and we will pick up with part 2 on this slide here.